So yeah, let me start. Sorry for the delay.
Yeah. Go ahead.
Yeah, today this work is done with the collaboration with Rosa Lopez Llorencera and David Sanchez in the institute called IFISC in Spain. And it's about how to realize a large efficiency quantum heat engine using some chiral quantum conductor and AC driving. So let me start with the motivation of work. So our motivation is what is a fundamental limit for the bound of the efficiency of the quantum heat engine limited by the second law. So here, there is a schematics of every heat engine that there is a heat reservoirs, hot one and cold one, and the working substance connected to them extract heat from the hot reservoir and dump part of it to the cold reservoir, and the difference is extracted to the external object in the form of useful work. So in macroscopic scales, the engines satisfies Clausius relation. So here the entropy production over a period is determined by the summation of the heat going into each reservoir divided by their temperature, because the working substance is always near the equilibrium. And this Clausius relation, identifying the entropy production in this form, and the second law that the entropy production should be non-negative always, determines the Carnot efficiency as a fundamental upper bound of the efficiency, which is just determined by the temperatures of the two baths and its universal value. But in microscales of the engines, as you know already well, it's easy to drive the system out of equilibrium. For example, as demonstrated in the experiments of Gillard engine using the quantum dots in this paper. And in some cases, they have shown that efficiency can be beyond the Carnot limit when you use, for example, like a coherence as a resource. And in this type of devices, it is important to identify what is the proper entropy production. And also there are limits when you drive the bath out of equilibrium. For example, as shown in these two works, here Rafael Sanchez and Robert Hiltney showed non-equilibrium demon and efficiency beyond Carnot limit, and also Scully, this pioneering work. Then our specific motivation is what is the effect of non-equilibrium bath when we drive this using the AC time-dependent voltage. And such study is desirable and timely because high-frequency AC experiments have shown remarkable ability to control and measure electron excitations in solid-state devices. Here is the example of the leviton, so-called leviton. And for example, here is the one-dimensional quantum wire, and you apply time-dependent voltage on one of the terminal, and it usually generates a lot of electron hole excitation in a noisy way. But they have studied that if you apply Lorentzian pulse, then each Lorentzian pulse excites only one electron, not nothing about the whole excitations in a clean way. And this excitation also had been verified using the quantum tomography. And there are other types of these devices, so-called single electron sources, in analogy to the quantum single photon sources in optics. And these devices has applications in a lot of fields like electron quantum optics, for example, probing wave nature of the electrons, or metrology, for example, redefining the current electric current standards, or quantum information, realizing flying qubits. But heat and energy currents are in these type of devices are only of recent interest. So in this talk, I will show you that indeed AC-driven chiral quantum conductor can show efficiency beyond Carnot limit. So here is a setup. Again, we have a hot bath and cold bath and the working substance in the middle. The working substance now is a scatterer, which have an energy-dependent transmission. And now we apply AC field to the hot bath, the hot AC voltage. Then this AC voltage generate dynamically electron hole asymmetry, as the example that I showed you, the diabaton case, only exciting electrons, not the holes. And this enhance thermoelectric current. But here, the AC field generally injects power to the electron, I mean, the working substance. For example, consider the Joule's law, and then the power should be determined by the square value of the AC voltage. Then this should be positive quantity, which eventually dissipates into the form of heat into the reservoirs. So this input power hinders the efficiency enhancement because now we have to subtract this input power in the total generated work to the power generated by thermoelectric current. But we found out that if we realize AC driving in a certain way, in a chiral way, then this power injection completely vanishes. So what I mean is that we apply AC field to the electrons propagating in a certain direction towards the working substance, not to the electrons propagating in the opposite direction. And this was a key factor for finding remarkable efficiency enhancement. And this chiral AC driving can be realized using chiral conductors, for example, in the quantum hall setups or topological insulators. Then the bulk is insulating phase, and electrons only propagates chirally through the edge states. And if you prepare the two contacts for the hot reservoir, and if you apply AC voltage to the only one of the reservoir contact, then you realize the chiral AC driving. And in the following results, I will show you the results using the AC voltage in the form of Lorentzian. And we only consider the time average quantities, the currents of charge, heat, and energy, not the time resolved quantities. So here is the result. The color shows the efficiency divided by Carnot efficiency. And here y-axis is the AC frequency of the voltage. So you can see when increasing the frequency, you see the enhancement of the efficiency. And remarkably, it can be even beyond the Carnot efficiency, as indicated by dark red colors here. And this was accompanied by negative entropy production, but when assuming Clausius relation, this quantity, as shown by the blue in this graph. So this seeming violation of the second law of thermodynamics could be resolved when adopting the Shannon entropy flow as the proper entropy production. Actually, in previous studies by Ponopen and Arachia, they have shown that when this quantum scatter is driven by fast AC, then Clausius relations can be violated, and this type of quantity rather identifies the entropy production more in an appropriate way. This is basically counting the Shannon entropy function for each ingoing and outgoing energy occupation for each reservoirs. And then we can also generate power even when all the baths has the same temperature, because again, we are violating Clausius relation. And the role of the AC voltage here is that it induces more uncertain energy distribution. It arranges the electrons in a more uncertain way in the energy space, but without injecting any network over a period. And then this kind of raise effective temperature, if you wish, and then it induces enhancement in the thermoelectric current. And then this can be useful for power generation, violating Canbian-Planck's statement of the second law. And in this case, the power generation is allowed up to some bound, which is determined by how much the Clausius relation is deviated, rather than the Carnot limit. And this kind of power generation or enhancement of efficiency beyond Carnot limit does not depend on the detailed forms of the AC voltage. So if you can just apply sinusoidal signal rather than complicated Lorentzian shape, you will still see this enhancement in the efficiency. So here is the summary. Yeah, so I will conclude here. Thank you.